welcome to the course Advanced Reaction Engineering. So, today we will discuss about the steady state non isothermal reactor designs. Already we have started this is the continuation of that course in this chapter. So, here today we will discuss about one numerical problem or example for the steady state non isothermal reactor operations. So, there how the conversions when we are conducting inside of the reactors. So, then there would be the changes of the temperatures inside of the reactors if we conduct that, let us say it is adiabatic operation is there. So, then either depending upon the reactions, whether it is exothermic or endothermic reactions, either temperature increase or decrease with progress of the conversions. So, that will check means how temperature conversions rate of the reactions, that is varying along the length of the reactors or volume of the reactors. So, that profiles will discuss by considering one numerical problem. So, here so the designs first we will consider the reactor is adiabatics. So, for this particular adiabatic reactors, that may be plug flow reactors or maybe packed bed reactors, either one. So, in case of the plug flow reactors, volume will come, and in case of the packed bed reactor, weight of the catalyst will come into the design equations or along the down of the reactor. So, with the increase of the catalyst weight, the conversion temperature rate that will vary. So, that profile basically will discuss means conversions. First we will consider plug flow reactors, and based on that other reactors, packed bed reactors will discuss. So, if we consider, let us say here a diagram is shown. See here let us say this is a reversible reactions that if we want to conduct inside of a reactor, that is a plug flow reactors. So, A is going to be the reactions is reversible reactions. So, the reactions will be conducted inside of the reactor in adiabatic operations, means there is no heat input output from the systems, even mass also in out, there is no mass in or mass out. So, when the systems will be operate, the reactions may be exothermic or endothermic. So, if it is exothermic, then for a particular conversions we need to progress, then so along the length of the or volume of the reactors. So, initially it was 0 at this particular point, when reactions will progress, then the conversions gradually will increase at different locations in case of the plug flow reactors. So, here in the step 1 what we will do means we know the design equations for a plug flow reactor. This is the differential equations, design equations for plug flow reactor or the mole balance equations. So, that we have to consider here, these are the component is the rate for this particular reactions we have to find out. So, how to find out the rate? In the step 2 we have to know the rate law. This is the rate law equals to for the reversible reactions is going to be that is the reversible reactions, small k that is the reaction rate constant, Ca that is the concentration of the reactant A, and Cb is the concentration of B. And Kc is the equilibrium constant. So, that is that particular temperature. So, that we have to put. So, here at the beginnings we are assuming that there is no fractional volume change for the reactions, and pressure is P equals to P naught this. So, under these conditions, so how to get the rate? So, here concentration of the A, that is also with the progress of the reaction that will vary, that we can measure, but at the same time the reactions rate parameter, that is the reactions rate constant, that is the small k and capital Kc, these are the also will changes along the length of the reactor I said. So, along the length of the reactor when progress is there, depending upon the exothermic reactions or endothermic reactions, temperatures will increase. If it is exothermic reactions, if conversion gradually increase along the down the reactors, the temperature will increase in the systems, and if it is endothermic reactions, then temperature of the reacting mixtures would be down. So, along the length temperature will be down for endo, and for exothermic reaction temperature gradually will increase. Okay. So, once systems means we know the rate or rate constant as a function of temperatures. So, this is the equations that already we have discussed many times. So, here activation energy rate constant, and that is the specified temperature at that particular temperature, reaction rate constant is known for this particular reactions. So, at T1 temperature if K1 is known, then let us say initially that this is the small k1 at temperature T1 is known. So, then when reactions will progress, then K2 at particular temperature would be there. This temperature will vary along the length of the reactors. So, at let us say it is initially it was 300 degrees centigrade. So, when progress of the reaction exothermic reactions is there 330 degrees centigrade, 350 degrees centigrade, that way the reaction temperatures will vary. If reaction temperature is vary, then reaction rate constant also will vary, since it is a function of temperature. So, this particular temperature will vary. So, therefore, at different particular specified conversions, if we know the reacting mixture temperature, that we can put it here, and rest of the other parameters are known, then reaction rate constant at that particular temperature is known. So, then that K we can put it here. Okay. And at the same times the equilibrium constant K c, this K c is related with this is the equilibrium rate constant. So, K c at a particular temperature, let us say when reactions will conduct at the temperatures, reaction or reacting mixture temperature will be different from the before and after the reactions. So, then if we know K c, that is the equilibrium constant at specified temperature is given, T2 is given, and that particular T2 temperature K c also at T2 temperature is given. So, then K2 is given, T2 is given, and reactions rate constant if we know, and heat of reactions for that particular reactions if it is known, since we know reactants A and B. So, its heat of reactions for that particular reaction reactant components are known, then heat of reactions changes for this particular reactions is known, that we can put. So, only this part here I said when reactions is exothermic reactions. So, this way reaction temperature will change, means initially it was that when progress of the conversion is there, the reaction temperature or reacting mixture temperature will be different. So, this value the temperature what we put it here, the same value we will put it here, then corresponding equilibrium constant K c, that value also will get. So, this value we can put it here. Okay. So, at that specified temperature, means known temperature K c value is known, when temperature is known K c value is known. So, when unknown temperature, if you want to know the K c value, K small k value, so that using these two equations we can find out. So, we can put it here, and from the stoichiometry relationships we know concentration as a function of temperature, how they are related for component A, component B. So, we know if x is the specified conversion, that may be any concentration, that may be 0 to 100%, any 10%, 20%, 30% x value, that is 0.1, 0.2, 0.3 like that up to 1. So, this is the fractional changes of or conversions. So, 10%, 20%, 30% or 100% conversion. So, if conversions at a specified conversions, that we want to know what would be the temperature. So, then that temperature is known, and then initial feed temperature and this temperature, this and this temperature, that particular conversions, if conversion is let us say 10%, on that time if it is exothermic reactions, the temperature what would be, that we can put it here. Then these are the components also we can put in the rate law equations, then rate law, combined rate law would come like this equation 2. So, by putting almost all components, means these equations and other components we need. So, then this would be the rate equations for particular reactions, means step 2. So, now since the reactions is equilibrium reversible reactions, so then at equilibrium the rate would be 0. Okay. So, once if we put this is combined rate equations or rate law we have derived. So, if we put this equals to 0. Okay. So, then after rearranging these equations, equation 2 we can get this. So, x is the equilibrium conversions and K c is the equilibrium constant at that particular temperature. So, if we know K c value at different temperature, then equilibrium conversions at that particular specified temperature what would be, that we can easily find out using these equations. Okay. Equilibrium conversion, this way we can find out. So, this is from the material balance. So, how means material balance equations, here K c is the as a function of temperature that I discussed here. So, as a function of temperature K c. So, here's now we talk about or discuss about the energy balance equations. Okay. So, the energy balance equations for general systems we have discussed. So, now in that equations energy balance equations, if we put Q equals to 0, Ws equals to 0, since the systems is a adiabatic system. So, then heat transfer rate in or out, rate of heat input or output, that would be the 0, and there is no shaft work. So, therefore, these equations also we have discussed in your previous lectures also. So, here's conversions and the reaction temperatures, how they are related. This is the reaction temperature and this is specified conversions, and these equations we can write this way also. In the left hand side we are putting temperature and right hand side we are putting x, same equations, but here left hand side x and here left hand side temperatures, right hand side x and here right hand side temperature, just rearranging the same equations in different way, both are the same for the energy balance equations. Okay. Now, if we assume that here we have taken, this is our reactions, two components are there might be inert component also may be present. So, here if we assume that heat capacity changes between A and B is 0, means there is no significant changes of heat capacity or almost close to same value. So, then this part we can eliminate, this part we can eliminate. Okay. So, and heat of reactions, this heat of reactions, so it is equals to heat of reactions at product minus heat of reactions reactants. So, similarly heat capacity also product minus reactants, this way also we can express. Okay. So, this is useful to find out heat capacity changes for particular reactant to product and heat of reactions for a particular reactions from when it is changes from reactant A to product B. Okay. So, these are the equations we have to use to find out heat, different components in these equations. Okay. So, now these equations we can simplify this way. Okay. So, just we are putting this part equals to 0, this part equals to 0, and this part heat Cpi and Cpi we can put sigma theta I Cpi and T0. So, this way you can write, if you simplify this equation it would become equation 3. So, here T0, that is the feed temperature at which the reactions or reactant mixtures we are entering or putting here. Here's starting temperature T0, at what temperature we are feeding the feed inside of the reactors, and Cpa value for the components, since here A and B these are the two components. Here component A heat capacity if it is known you have to put, and heat of reactions for this reactions if you know. So, then that we can put it here at that reference temperatures. So, then all components are known except x and t. So, this is a function of conversions and temperature, how they are related using equation 3. So, if we change x equals to 0.1, 0.2, 0.5 like that, so then the temperatures inside of the reacting mixtures accordingly will change. Okay. So, this is the way, means objective of this energy balance equations to know at a specified conversions what would be the inside temperature of the reacting mixtures. Okay. So, now using means this equation 3, equation 2, this is the red equations, and equation 1, that is the design equations. So, mole balance equations. So, we have a mole balance equations, we have red equations and we have energy balance equations. So, these three equations we can solve simultaneously or numerically also we can solve for a, since our reactor is the plug for reactors. So, this is the design equation, integral form of design equation to find out the volume of the plug for reactor. So, this type of equations we have discussed in at the beginning of our lecture. So, here's if we want to know from 0 to x, that may be 75% conversions or maybe 60% conversions for a particular reactions if you want to achieve. So, then what would be the volume of the reactor, that we can find out. So, for that we have to find out, before that F A naught by minus R A, that we have to find out. Okay. So, here's once we know that, then we can integrate from 0 to that specified conversions. After integrations whatever the value will come, that would be the volume of the reactors. Okay. So, this we can solve numerically to find the volume of the reactors for plug flow reactors. Here we have conducted the reactions in a plug flow reactors, or else this is the way 1 or way 2, means either this or this we can use. So, numerically we can solve it, or or else we can use ordinary differential equation solver to solve equation 1, 2, 3 and find the volumes. Simultaneously we can solve that by putting all known parameters that is required to solve those. Okay. So, now let us say if we consider this is our reactions, adiabatic operation is there, and this is feed temperatures. Let us say at that temperature we are putting that feed injecting here, and reactions will take place let us say at 360 degree centigrade, and conversions will progress like this 0 to 90% conversions, and the operation is the adiabatics. Okay. So, here's means I said it is we can solve numerically to find out the volume. So, we have a design equation plug flow reactor is this, and this is our reacting system. So, in the step 1 this is let us say feed inlet temperatures we know. So, for one particular point, means let us say this way we can the reactors we can say that from here x equal to 0. So, here 20% conversions, here 30% conversion, like that, here 90% conversion, that way it would progress in case of the plug flow reactors. So, then let us say for example, when 20% conversions is there, when feed is at this temperature we are entering inside of the reactors. So, then when at this conversion, so what would be the temperature inside of the reactors. So, if heat capacity of the component A is known, heat of reactions is known. So, how to calculate those things, so already have discussed. So, individual component enthalpy and heat capacity if we know. So, then the difference of heat capacity or heat of reactions for that particular reactions we can find out. So, now this heat of reactions we know, Cpa for component A is known, and Xa value, that is initially we can put, that is 20% conversions. For that we are want to find out the temperatures, we want to evaluate the temperatures, this part we can want to evaluate. So, this temperature is known, this is the feed temperature 330 degree centigrade, this part we can put, this part we know, this part we know, x part is 0.2, 20% conversion. So, then T easily we can evaluate, okay, for at a 20% conversions. Okay. So, what would be the temperature when conversions was 20%, that we know. So, by putting all known parameters. So, now reactions rate constant we can find out similarly, temperature we have evaluated by using energy balance these equations, this temperature now it is known for 20% conversions. So, now we put these temperatures, that may be let us say 350 degree centigrade. So, this T we can put 350 degree centigrade, T1 is given for at a given temperatures, that is T1, corresponding reactions rate constant is given, means for this particular reactions, if the reactions if you conduct any temperature T1 temperature may be 340 degree centigrade. So, Q1 small q1 that is known at 340 degree centigrade is known, this value is known. So, this value you can put it here, this is known, activation energy for this reactions is known, R value is known, and T1 that is also already is known. So, then small k at this temperature is known. Okay. This is the unknown temperature that was evaluated from the energy balance equation. So, now small k value is known. Similarly, Kc value, equilibrium rate constant value at that specified temperatures, means when conversions is 0.3, then reactor temperature is this, that we have evaluated from the energy balance equations. This value also same temperatures we can put it here. Okay. And T2 value at a given T2 value, equilibrium constant that is also known. So, then this part is known and this T2 part is known, and T value we have find out, this is 350, heat of reactions that we know, we can put, R value is known, then Kc at specified temperature that we can evaluate. Okay. So, Kc value we can find out by using equation step 3. So, now we know small k value at that reaction temperature, Kc at that particular temperature, and what would be that temperature at when conversion is 20%. Okay. So, this way we can find out all components at that particular temperature. So, when Kc value is known, Kc at particular temperature, that is known or we have find out. So, then Kc value here and here we can put, and then if we solve it, then equilibrium conversions, since the reactions was reversible reactions, what would be the equilibrium conversions we can find out. Okay. So, now we have to find out step 5, that is the rate of the reactions we have to find out. This is for this particular reactions, what would be the rate. So, here small k value we have find out, Ca naught initial concentration of the ray A, that is we are putting or charging inside of the reactor, that is known, and conversions already specified, that is 0.2 20% conversions. Kc value already we have known, that value we have find out at that particular temperature, Kc at T that known. Okay. And then T0, that is the feed temperatures, and this T also we have find out from the energy balance equations. Okay. So, all components in the rate equation is known, then we can find out rate at x equals to 0.2. So, when conversion is 20%, then what would be the rate we can find out. So, similarly at the same times in the step 6, molar feed rate of component A is given, then with that minus Ra we can divide. So, we can get Fa naught by minus Ra. So, this value would be known, Ra we have find out, and Fa naught given. Okay. So, molar feed rate of that component A inside of the reactor, that is known. So, then this value we can find out. Okay. So, it was evaluated for 20% conversions. So, here see, so the things what we have find out, x equals to when 20%, I am summarizing the component of things what we have evaluated. So, when conversion is 20%, then the reactor temperature would be this, but at the temperature the feed temperature would be let us say 300 degrees centigrade feed temperature. At this temperature we are feeding the feed, and on that times when reaction has progressed 20% conversion, then inside of the reacting materials temperature would be higher, since the reaction is exothermic, and on that times small k or reactant at this particular temperatures, this k value is this, and at this particular temperature Kc value is this. So, Kc value also we have this using step 2 and step 3, small k and capital Kc value we have find out. Okay. So, now equilibrium constant also equilibrium conversions also we have find out using this step 4, and minus Ra, that is in the step 5 we have find out rate. Okay. So, when conversion is this, rate would be this, and Fa naught, that is I said it is, if it is given, then Fa naught by minus Ra, that we can find out this. So, 20% when conversions is there is this, but I said for this particular reactions, if you want to know 0% to 90% conversions, then what would be other components. Similarly, for 0.4, this value, this value, this we can find out. Similarly, 0.6 means 60% conversions also, these are the components we can find out. Similarly, for 80% also we can find out the all components by using following step 1 to step 6. Similarly, for 90% also we can find out all these components. So, individual conversions, if we 0 to 90% conversions, if you want to conduct for this particular reactions in a adiabatic mode inside of a adiabatic reactor. So, then with exothermic reactions, progress of the reactions, the temperature will vary this way, rate constant, reaction rate constant will this, equilibrium constant will be Kc will vary this way, equilibrium conversions will vary this way. If we, this is the table we have developed by using all these equations. Now, if we plot them, okay. So, means using these equations, Fa naught by minus Ra we know for 0% to 90% conversions, this is 0% to 90% conversions. Similarly, see this Fa naught by minus Ra value we have evaluated. Okay. 0.2 the sample calculation I have shown. Similarly, 0.4, 6, 0.8, 0.9 value is this. So, this is F A naught by minus R A by minus R A. At the beginnings we have discussed this, if volume is this, okay, or conversions, let us say conversions 0% to 90%. So, it would be like this is 0 and this is 90% conversions. So, this would be 90% conversions this way, this is the area under the curves. So, this area under the curves would be the volume of the reactors, that at the beginnings we have started this. So, using this means integrating by using Simpson's 1/3 rules, we can evaluate what would be the volume of the reactors. So, now if we plot from this data, from this tables, what are the data we have, that we want to plot, we want to see the profile. Okay. So, conversions versus volume, this is the conversions point 0 to 90% conversions and corresponding volumes. So, volumes x axis we can put. Okay. So, then conversions would be like this. If we know that particular temperature progress, this is the temperature, means inside of the reacting mixtures. Similarly, x axis if we put volume of the reactors, so then how rate is varying. So, that also this way it would vary. So, easily we can find out. So, here in the red equations two components are there. So, this is for a small k and this is for capital K, two components are there. So, at the beginnings you can see small k value, it is gradually increased very fast, and Kc value not that much significantly, it is decreased, but not that much, means 3.1 to 2.5, but here 4.2 to 31.67. So, small k value progressively increase. So, therefore, this part component A part gradually increase, and then it is with increasing temperature. Since this here you can see the temperature with progress of the reactions inside of the reactor gradually increase, since the reactors is reactions is exothermic reactions. So, then rate would that will it is vary, rate will drop. Okay. So, this way we can express means how the profile, means conversion versus volume, temperature against volume of the plugged for reactors, rate of the and volumes how they are varying. So, it would reach to the maximum, then it would drop. So, this is the numerically we can solve, means individual points you have to find out, and this table you have to develop, and once we have these tables, then we can use these equations, and by using Simpson's 1/3 rules numerically we can evaluate what would be the volume of the reactors and what are the profiles, temperature profile, conversion profiles, rate profiles along the down of the reactors or volume changing of the reactors we can find out. So, in the second, this is the case 2. Case 2 means the same equations, means by using software ordinary differential equation solver we can solve this. Okay. So, here all the components 0 to 90% conversions, we do not have to put individual points to find out that respective temperature, rate constant, equilibrium conversions rate, this. So, just these are the equations we know, this is the differential equations, design equations or material balance, mole balance equation, this is the rate equations, and for this rate equations these are the components parameters is there. Okay. And this is the temperatures. So, that we have to put here, means equation 1 to 5, equation 1, 2, 3, 4, 5, all 4 equations we have to put in the ordinary differential equation solver, and respective components value, numerical value or initial guess value, that we have to supply, and then once we means enters, these are the parameters I said. So, these are the component parameters we have to provide in the ordinary differential equation polymath or similar type of ODE solver is there. There we can put these are the parameters, numerical value, and these are the equation 5 equations we have to put, and then we have to run. Then initial guess value is this, x equal to 0, volume equal to 0. Then after running, so these are the call components value we can find out or we can get, and that profile should come like this. Similarly, here if it is exothermic reactions, volume temperatures it would be nature would be like this, conversions and volumes it would be like this, and rate and against volumes it would be like this, that already have discussed. And if A is going to be these reactions, initially we have considered exothermic reactions, then the nature should be or temperature profile, conversions profile would be like this. If reactions is endothermic reactions, so then the nature would be like this, if it is endothermic reactions. So, conversions and volume, conversions will progress along the length of the volume of the reactors, then the temperature inside of the reactors that will drop drastically this way. Here it was increased since the reactions was exothermic, therefore, inside of the reactor temperature gradually increase, and when it is endothermic reactions the temperature inside of the reacting materials will drop or decrease. Similarly, rate of the reactions it is also will decrease, and at this time there is no rate, means reactions almost will be completed, or no progress of the reactions, means rate close to 0 would be there at the end of the reactors. So, this is for endothermic reactions, and these are the for exothermic reactions, the temperature profile, conversion profile, rate profile for this way, means ordinary differential solutions or solver that we can use to find out. So, today what we have discussed for reversible reactions or adiabatic reactions, how to find the conversions volume profile and temperature profile with volume of the reactors and minus area against volume. Okay, so, how means for these three profiles we have find out or evaluated, numerically we can solve, or by using ordinary differential equation solvers we can solve to find out this and this profile. Okay. So, depending upon the means here's material balance and energy balance, both the equations we have to use to find out the profiles. Thank you. So, today is up to this. Okay.